before we talked about the mean of a discrete random variable as being the expected value of x, and that was going to be a weighted sum of all the values that x could take on by the weight that they might actually occur. That probability weight was our weighting factor. For continuous random variables, it's analogous, except for instead of discrete sums, instead we're going to take an integral. And in many ways, what we're really doing is the same kind of thing. Here's the possible value of x, and it's going to be weighted by probability density times dx. So that in itself, that dA right here, is a probability, and we're going to take then that moment, or take that x value times that. And that's an important notion, that idea of moment that I just mentioned. So let's draw out a probability density similar to what we did with the traffic gap problem. Keep coming back to that one. And I'll switch variables here on you to t. Doesn't matter, of course. And in our case, that ran up at 9 to a peak, and we have a symmetric distribution, total base at 18, and that total height was 1/9. Remember that our physical kind of idea was, gee, this is just a centroid, or a center of mass, and because of the symmetry, we know that that has to happen right about there, and therefore our mean for this particular variable is 1/9. But how do we prove it? And there's two things I want to point out. One, that as you look at this x value right here, or t value, as the case might be, that's our moment for this little area that's sitting here. Right? That's the moment arm from 0. Right? So that's that notion of why this is a first moment of the area, or sometimes we call the mean the first moment of the distribution. Okay? It's also how we get to the notion that, gee, that's like a centroid, because if we think about that as the distance to the centroid times the total area, remember that's how in statics we talked about this whole thing, and we wanted to find the centroidal distance, well then we just divided all of this, the first moment of the area, by the total area, and that gave us that. And oh, by the way, that total area, because it's a probability density function, has to be 1. That even kind of sets that in a little bit further of that kind of notion. So it is very easy and obvious to see that in this case, mu, it's at the centroid, geometric centroid, or the mass centroid, depending on how you want to look at it, and that equals 9 seconds for this particular example. Yeah, you could work out through all the math, and the book does that for a couple of problems, but that math is really only very easy for some very select probability density functions. Hence, recognizing some of the geometry that we might have, such as in the triangle, is very useful to us. Okay, let's look at one more property that we commonly are interested in, and that's the spread, or the variance, for our continuous random variable. Right, and as before, with our discrete, as a review, our variance looked like sigma squared equal to the variance operator, and that in itself was equal to the expected value of the squared deviations away from the mean. And from an integral calculus approach, that means we're going to integrate over all x, those squared deviations, times the probability that they happen in that area. And so if we go back to what we've got here, that squared deviation. Well, there's your deviation. There's your mu, and there's your t. So t minus mu, substitute in t minus mu, quantity squared to get rid of the plus or the minus on either side, right? That's why we square this whole thing. We want to see how spread away this area is from the centroid, right? Times the probability. That's that dA business all over again. Another way to think about it. Now the book is going to show you how you can expand this and then simplify it and maybe think about it in a different way, just like we did over here, and it'll come out to the same kind of thing, that you could look at this as the expected value of x squared minus the square of the mean. And if you'd rather, then you do a different integral of x squared fx dx, and then minus u squared would be another way to process that if you wanted to. The thing that interests me out of all this is what geometrically the expression means right up here. And notice that before, to find the centroid, that was the first moment of area, right? Right, down here, we're at the second moment because we're taking it squared, and because our reference is mu, it's with respect to the centroid. Oh, wait a minute, there's another geometric analogy here, and that is that the moment of inertia of the area, the second moment of area, was just that. It was the integral of, well, if we're doing it with respect to the centroid, that'd be that I bar, that'd be the x minus our x bar squared dA. And further, when you did that, we talked about also the radius of gyration being the square root of the centroidal moment of inertia, or the second moment of area, divided by the area. Well, guess what? Here, once again, we have the special case where that's equal to 1.0 for our case. So what you end up with is that our radius of gyration is equal to the square root of the variance, and that, by definition, is our standard deviation. It's a very nice, powerful way to think about what the variance is. And if we come back then to our triangular distribution up here, this isosceles triangle, we find out that the spread, or the radius of gyration, is going to be equal to b over 2 root 6. Yeah, that's if I've done my math properly. I always encourage you to check that out. B is our base. So 18 divided by 2 root 6. And if you want to know what that is, well, gee, take 9 divided by 6 root, and we get 3.67 seconds for our standard deviation. And because you know I am so interested in relative spread, remember the COV, coefficient of variation, sometimes has the symbol delta, little delta that is, would be equal to the standard deviation divided by the mean, and that in this case would be 9 divided by 3.67 divided by 9, and of course that'll be more than 1/3, 3.67 divided by 9, and we get 0.41, or 41% COV. That's a pretty large relative spread, but maybe you have a case where that is what you've got going on.